Let me begin by asking you to do something deceptively simple. Look at a clock, any clock. Watch the second hand sweep its circle, or the digits flick forward, one by one. Each tick feels identical to the last. Each second seems to arrive with the same faithful regularity, as though time itself were a metronome set at the birth of the universe, never wavering, never slowing, never rushing ahead. You feel it in your bones, the steady, reliable river of moments carrying you from past to future. It seems so obvious that it barely deserves mention. Time is time. A second is a second. What could possibly be controversial about that? Everything, as it turns out. Everything. In 1905, a 26-year-old patent clerk in Bern, Switzerland, dismantled this most basic of human intuitions and rebuilt reality from the ground up. His name was Albert Einstein, and the theory he published, that year the special theory of relativity, didn't just change physics. It changed what it means to exist in this universe. It revealed that the clock on your wall, the watch on your wrist, the steady beat of your heart, none of them are measuring what you think they're measuring. Time, Einstein showed, is not a river. It is not universal. It is not even the same for two people standing in the same room, though the difference between them is so breathtakingly small that no human sense could ever detect it. But make no mistake, the difference is real. And when you scale it up, when you trade the leisurely speeds of everyday life for velocities approaching the speed of light, that tiny difference becomes a chasm wide enough to separate families by decades, wide enough, perhaps, to make a round trip to Mars, not merely dangerous, but, in a sense that Einstein would have understood with painful clarity, irreversible. Richard Feynman, the great physicist and legendary teacher, once reflected on this problem with characteristic bluntness. He pointed out that the physics of relativity is not merely a theoretical curiosity, it is a concrete, practical constraint on what human beings can and cannot do in this universe. The faster you travel, the more time bends around you, and the consequences are not metaphorical. They are as real as the ticking of that clock you just watched. Feynman warned that when we dream of interplanetary and interstellar travel, we must reckon with the fact that the travelers and the people they leave behind will age at different rates. The astronaut who departs Earth as a young woman may return to find her children older than she is. The crew that sets out for a distant star may come home to a civilization that has forgotten their names. This is not science fiction. This is science, and it begins with two deceptively simple ideas. Einstein built his entire theory of special relativity on just two postulates, two statements, that's all. The first is the principle of relativity, and it says something that sounds almost boringly reasonable. The laws of physics are the same for all observers who are moving at constant velocity relative to one another. If you're sitting in a perfectly smooth train, gliding along a straight track at constant speed, and the blinds are drawn so you can't see the landscape passing, no experiment you could perform inside that train dropping a ball, pouring a glass of water, bouncing light off a mirror, would tell you whether you're moving or standing still. Motion, at constant velocity, is undetectable from the inside. This is something Galileo understood 4 centuries ago. It is intuitive. It makes sense. If you've ever sat in a parked train and felt a jolt of confusion when the train beside you began to move, unsure for a moment whether it was you or them that was in motion, you've experienced this principle firsthand. The second postulate is where everything goes sideways. Einstein declared that the speed of light in a vacuum is the same for all observers, regardless of how they are moving relative to the source of that light. This sounds innocuous, perhaps even dull, until you sit with it for a moment. Think about what it means. If you're standing on a platform and I drive past you at 60 miles per hour and throw a baseball forward at 30 miles per hour, you would measure that baseball traveling at 90 miles per hour, my speed plus the ball's speed. This is ordinary addition. This is how velocities work in everyday life, but light refuses to play by these rules. If I drive past you at half the speed of light and turn on a flashlight aimed forward, you do not measure that light traveling at 1.5 times the speed of light. You measure it at exactly the speed of light. The same speed I measure it at, the same speed every observer in the universe measures it at, no matter how fast they're moving, no matter which direction they're headed. The speed of light is not relative. It is absolute. It is the one fixed point in a universe where nearly everything else depends on your point of view. Now, This should disturb you. If it doesn't, you haven't thought about it carefully enough. Because the arithmetic of everyday life, the simple addition of velocities, is built on assumptions about space and time that Einstein's second postulate demolishes. If the speed of light is the same for everyone, then something else has to give, and what gives, as Einstein realized with an insight that borders on the terrifying, is time itself. But before Einstein arrived at this conclusion in 1905, the constancy of the speed of light had already been demonstrated experimentally in one of the most famous and consequential null results in the history of science. In 1887, Albert Michelson and Edward Morley set out to measure something that every physicist of their era believed must exist, the luminiferous ether. The prevailing theory held that light, like sound, required a medium through which to propagate. Sound needs air. Ocean waves need water. Light, it was thought, needed the ether of ghostly, invisible substance pervading all of space. And if the ether existed, then the Earth, hurtling through space in its orbit around the Sun, must be moving through it, creating a kind of aether wind. Michelson and Morley designed an exquisitely sensitive instrument called an interferometer, which split a beam of light in two, sent the halves along perpendicular paths, and then recombined them. If the Earth were moving through the ether, the light traveling parallel to the direction of motion should behave differently from the light traveling perpendicular to it, just as a swimmer crossing a river against the current takes a different time than a swimmer moving with and against it. The two beams, upon recombining, should have been slightly out of step. There should have been a telltale shift in their interference pattern. There was nothing, no shift, no difference. No matter how they oriented their apparatus, no matter when they conducted the experiment, the speed of light was stubbornly, impossibly the same in every direction. The ether wind did not exist. The ether itself, it seemed, did not exist. The result baffled physicists for nearly 2 decades. Various explanations were proposed, including the idea that the apparatus itself was physically contracting in the direction of motion, an idea that turned out to be partially correct, though for reasons no one yet understood. It took Einstein, approaching the problem not from experiment, but from pure thought, to see the answer clearly. The speed of light is constant because the universe is built that way. It is not a quirk, it is a law. And if you accept it, truly accept it, the consequences cascade like dominoes. To see the most dramatic of those consequences, let us conduct a thought experiment. Imagine the simplest possible clock, a device so elegant that its mechanism lays bare the very nature of time. Take 2 perfectly parallel mirrors, mount them facing each other about 1 meter apart, and bounce a single pulse of light between them. Each time the light strikes one mirror and bounces back to the other, the clock ticks. Since the speed of light is constant and the distance between the mirrors is fixed, each tick takes exactly the same amount of time. This is a light clock, and it is the purest timekeeper imaginable, because it relies on nothing but light and distance, the 2 pillars of Einstein's universe. Now, place this light clock on a spaceship. The ship is floating in space, engines off, and inside the astronaut watches the pulse of light bouncing straight up and down between the 2 mirrors. Tick, tick, perfectly regular, perfectly normal. Now imagine that I am watching this scene from outside, floating in space myself, as the ship glides past me at tremendous speed. What do I see? From my perspective, the light clock is moving sideways. The pulse of light is still bouncing between the 2 mirrors, but because the entire clock is moving, the light is no longer traveling straight up and down. It's traveling along a diagonal path, up and to the right, then down and to the right, then up and to the right again, following a zigzag as the ship moves past me. And here's the crucial point. Each diagonal path is longer than the straight vertical path the astronaut sees. The light has farther to travel between each bounce. But, and this is Einstein's second postulate, the postulate that changes everything, the speed of light is the same for me as it is for the astronaut. I cannot see the light moving faster to compensate for the longer path. Light travels at light speed, always, without exception. So if the path is longer and the speed is the same, then the time between each tick must be greater. The moving clock, as I observe it, ticks more slowly than my own clock. The astronaut's time, as measured by me, has stretched, dilated. Seconds aboard that ship are literally longer than seconds in my frame of reference. This is time dilation, and I want to be absolutely clear about what it is and what it is not. It is not an illusion. It is not a trick of perception. It is not that the moving clock merely appears to tick slowly because of some delay in the light reaching my eyes. The moving clock genuinely, physically, measurably ticks fewer times. If the astronaut counts 100 ticks of her light clock, I might count 150 ticks of mine during the same interval, and when we compare notes later, we will agree she aged less than I did. Her biological processes ran more slowly, her heart beat fewer times, her neurons fired fewer signals. She is younger than she would have been had she stayed behind. And yet, and this is the part that tortures the intuition from her perspective, everything aboard the ship was perfectly normal. Her clock ticked at its usual rate. Her heart beat at its usual rhythm. She felt no slowing, no stretching, no distortion of any kind. Time dilation is not something you experience. It is something that happens to you as observed.